So let us put a handy box around our two new key equations for describing inductors. And now I want to think a little bit about how we analyze them in a circuit. And this gets to be interesting, I think, because the electrical engineers have a very nice way of looking at this. Now, we've just said we have a new second Kirchhoff's law that says that the sum of the voltages around a closed loop is not zero anymore, right? It's going to be the time derivative of the magnetic flux through the solenoid. And what we've just learned is that magnetic flux is always going to be just some constant, this self-inductance, times the current I. So that if we rewrite this just slightly, you see then the inductance is a constant. It doesn't depend on time, so I can factor that out of my equation. So I have L times a di dt. Now this is a little different from what we've seen before, but it's not too dissimilar from like capacitor theory, right? In capacitors, you have something with the charge and a capacitance factor that acts like a voltage. Here, it isn't acting exactly like a voltage. It's ending up on the other side of the equation, and that's just a little bit awkward. So what the electrical engineers do is they have this nice mnemonic in terms of how they treat this term as an effective voltage. So what they tend to write down, but you have to be careful, it's not really a voltage, but for analyzing circuits, you kind of can pretend it is. So what they do is they write down an effective Kirchhoff's second law. So I'm going to put quotes around it, meaning effective Kirchhoff's law. And what they do is they try to make this as similar as possible to the traditional law. So what they do is they write it as 0 equals something, and 0 equals, we can see from this equation, the sum of the voltages around my circular loop, right, with an additional term. I have to subtract off this extra term, minus L di dt. And when we do things this way, you can see what we're adding up are all the normal sort of voltage terms, Q over C, IR, etc. But then when we come to an inductor, we add another type of term, an effective voltage term. It's not a real voltage, but it's an effective voltage. So we can really rewrite this in exactly the form you're used to using, which will make your circuit analysis very straightforward by adding up around a loop a set of effective voltages, which must always equal to 0. And that will work for us, provided we remember that the effective voltage associated with an inductor is equal to L times di dt. Now, notice I haven't spoken yet about the sign that goes in front of this. The sign, of course, always depends upon which direction you are summing your voltages around. Depending upon which way you sum things, you could end up with either a plus or a minus sign. So let's think carefully how we can remember and track that sign. There's a very nice mnemonic that goes with it. For our example, and the direction we've chosen to go in so far, most definitely the minus sign was correct. But here's how we can remember the direction of that sign. So I'm going to give you a little sketch here of an inductor. And if you think about the analysis we just carried through, we imagined having a current I flowing down through my inductor, right? That's what we had way up here at the top of our analysis. And when it came down here through like this, as we went around our loop in this direction, in the same direction as the current, it came out with a minus sign. So when we go with the current, it's a minus sign. And if you think carefully about it, that's the same thing that happens with a resistor. When you're going with the current, when you're going downstream, the term enters your equation with a minus sign. So to help us remember that, what we can do is we can take the inductor, right, and label it in precisely the same way we label the resistor, with a plus sign on the upstream side of how the current is flowing and a minus sign on the downstream side. And then we just remember, whenever we traverse from plus to minus, it's going to count as a drop or a minus sign in our equation. If we happen to be going the opposite way counter to the current, of course, it would flip the sign and we would end up with a plus sign. So the way I remember this term is to always, like I tell you, voltage across a resistor is not IR. It is plus or minus IR. Similarly, across a capacitor, it is plus or minus Q over C, and for an inductor, it's plus or minus L di dt. But if you remember to label it with an upstream plus and a downstream minus, the signs in your equations will always come out